Presented. Now we should.
Are we recording?
Probably now we do. But it's not very hard, and you may look for it as we speak. So this we do need to have some benefit for your practical research life from this course, not only get enjoyment from building orbitals. So, who ever did electrochemistry? Huh? Do not hesitate if you did. 1, 2. Who? Okay. Can you tell what it is? What is electrochemistry? Yes. Just informally define.
That's a kind of chemistry that deals with transfer of electrons and electrical.
But cyclic voltammetry.
It's redox interactions.
Okay, so what do you get? What do you get out of cyclic voltammetry?
Potential.
Huh?
Potential.
More specific.
The reduction potentials. There is a graph from which I have done that in my lab, but I don't know how to.
So it's something like.
Yes.
Yeah, exactly.
Right. What is x-axis? What is y?
There's potential.
Voltage and current. So if you are in physics background, it is like current voltage characteristic with hysteresis. Ben and Cage, you never heard about it? Did you took analytical chemistry right now?
Yeah.
And they didn't present it?
Not that I recall.
Okay.
They would have done it in lab. That would have been a lab experiment.
Yes, it's very popular experiment in chemistry. So, what is reduction and what is oxidation in terms of potential?
Gain of electrons is reduction. Oxidation is loss.
Everything is correct. David, you want to add something?
No.
Can you add something if you are mandated? Of course, you don't. About importance of connection of electrochemistry, cyclic voltammetry with ionization and electron affinity.
Is it like stabilization? Like how stable a system is, kind of?
You know, different molecules, or I should take war hat of analytical chemist, although I'm not a chemist at all. So, is it a new figure for you guys? So, for whom it is a new one? 1, 2, 3, enough to talk. So, what you do, it is major outcome of the experiment where you basically take like a battery, take variable resistance so that you can scan the voltage, take ampermeter that measures current, and then you put electrodes into the bath. And then in this bath you dissolve a molecule that you are interested in. I'm exaggerating and simplifying, but basically it's same like electrolysis, but with much smaller voltage, and you do not see like bubbles typically. It's analyzing dissolved molecules. Please correct me if I'm.
Is it measuring activity though?
It is exactly electrolysis. Electrolysis is just a specific form of it.
Okay. Okay. And then if you scan voltage, right? It is expected that if you increase voltage, current will increase, right? If you make negative voltage, current will be negative. So if you put just resistance, like a chunk of resisting material, it will be linear, Ohm's law. But if it will be like something different, it will be non-deviating from a line.
So it's you're measuring conductive properties of material.
Yes.
Okay.
But if it is not a material, if it is a molecule
Mhm.
with gap, with energy levels, then it will be very nonlinear. So at one wing, you will get a spike when molecule suddenly will start absorbing electrons instead of letting them go through. Okay? And it will be reduction. On the other wing, if you put voltage too high, it starts releasing electrons, and it will be ionization of molecule. And these peaks tell at which energies molecule is able to release or admit electron. So this analysis is important to project like electrolytic cells, photoelectrolytic cells, ability of molecules to come into reactions, right? To exchange electrons. So reduction and oxidation potential. So I'm telling things that I'm not a specialist in, but I was assuming that like everyone got.
What are the U and V axes again?
Potential, voltage,
Okay.
and current. It's not U, it's better I, current. Okay? Current and voltage.
You probably also say that potential is in reference to another.
Yes. Yes.
item.
There is a third.
Usually the standard hydrogen.
Yeah. There is a way to centralize it.
All right. This reminds me of an Ohm's law diagram, except voltage is on the y-axis, current is on the x-axis. So, is there any relationship between this and Ohm's law, or is it just a coincidence?
If instead of putting like electrodes into the bath with chemical, if you would put just a resistor,
All right.
then it will be a straight line.
Okay.
Okay? But it is very non-linear, non-straight line because of chemistry.
So it's an electrode, not a resistor.
Yes,
Okay.
it is something very more complicated. And this diagram will be different for each material.
All
So
right.
characterizing materials is electrochemistry. One of the ways. This reduction and oxidation energy is telling whether your molecule will be serving better as a reducing or oxidizing agent and many other things. So energy of ionization is how much voltage you need to apply to remove electron from a molecule. Energy of reduction is how easy to stick electron into the molecule, right? Good? Make sense? And they are abbreviated as ionization energy and electron affinity. So for removing electron, oxidation, and electron affinity is reduction. And then it's not a big thing to measure them in volts, right? Or electron volts.
And this relates to the Koopman's theory.
Yes, yes. So I'm assuming that everyone is already ready and dying to know ionization energy and affinity energy of any molecule. And it was one of the major reasons of you taking this class. Like if people with chemistry majors would take it, probably it would be one of them, right? No? So Koopman theorem tells that ionization energy is approximately equal to energy of HOMO, and electron affinity is approximately equal to energy of LU, calculated by either one of the methods, like for example Hartree-Fock. Of course, with different methods you will get very different energy of orbitals. Generally, Koopman's is wrong. It is like error can be like 50%. But as a starting point, if you have series of molecules and you analyze them with the same computational method, you'll get right trends. Yes?
Like, if you use more accurate functionals in the Hartree-Fock, does the Koopman's theorem start to be better at predicting actual values?
Yes, if you, but
Because I'm reading in Wikipedia that that's not really the case, actually.
if you really getting hired to compute ionization and affinity energy, you need to charge your system, literally, add or remove electron by changing charge and multiplicity in your, if you're doing Gaussian, right? And then compare total energy. Like ionization will be total energy of n-1 electrons minus total energy when you have n electrons. And electron affinity will be total energy of n+1 electron minus total energy when you have neutral reference number of electrons. Okay? So who is telling Koopman electron affinity on tomorrow's show? Let me check and bring it up. But it is like an important point that it's not yet late to bring it up if. Strange that it reopens PowerPoint. It was already PowerPoint. Okay, so it is a big intrigue. I wasn't remembering all these things. Yes. So it's your favorite subject from now on. Okay? Koopman's theory. So I know we are supposed to do more practical things like drawing orbitals, but there is no reason if we do not stay on the same page. Is it enough justification to look onto energies of Ohm and Wuma? Right? No objections. So for, yes?
What do you mean by n-1?
Removing electron, charging, with putting positive or negative charge. So I'm just suggesting for those unknown people who used wrong number in here to carefully track what is the number of Ohm and Wuma orbital, because it is critically important, right? So it is real observables that you can offer to your collaborators. No, don't take shots. So those are observables that you can include into papers. Or if you do screening by data mining, and you have like 1,000 molecules, you may want to compute this ionization and affinity for each of them and then use them in data science. So it is something that you can sell. You can put in your papers and get it published. Okay? And if you have forgotten which scripts to use to generate this file,
They're in the
so now I'm looking on slightly different system. So if you hate scripts or you have forgotten them, then you need to look on the line that splits occupied and virtual orbitals, look on the last occupied orbital and then count from here to there, like 1, 2, 3, 4, 5, and it is our old example with 24, right? But in each individual calculation, this number will be different, and it is what we need to find. So what is the number of whom, what is the number of whom, and then report their energies. Okay? So you already can like leave the class, forget about grade, and just be a freelancer making papers on computational chemistry.
We also get the total energy from the scan.
Yes. It's like keyword something like self-consistent field, SCF at the end.
I have a question.
Yes.
Related to my topic for the transition state search, that's just one thing.
Oh, I will cover it.
You will cover it.
It is, yes.
Because I was thinking you wanted me to make TDDFT.
No.
Okay.
No. Postpone TDDFT for a month and a half or 2 months.
Okay, because I'm thinking excited state calculations. that's the
No.
thing.
It will be too quick. So,
Okay.
Koopman theorem, and then those were just notes. Number 4, open shell orbitals. And number 5, scan of reaction coordinate. So I will try to make examples and invite you to follow them, because and later you may use the same or different examples for the presentations. But density of states, energy of HOMO, energy of lumen, and their offset is some very basic, very important information that like survival minimum. Right? Later on, some of you will face necessity to describe molecules that or materials that include transition metals. Right? And due to just laws of nature, the Aufbau principle becomes a little crazy when dealing with transition metals. Sometimes they get more energetically favorable configurations when shells are half filled, and they are filled with same spin projection. So number of electrons with spin up and spin down differ. So this thing that Mead mentioned as a joke, like draw orbitals and fill them with arrows, right? So what you were telling is to plot orbitals and put up and down, right? So I'm doing only the introduction, then I'll go in with tiny details. So this picture works only for, huh?
I was going to say diatomic.
No, not only diatomic. For any right word, it starts with letter S.
Shell.
Closed shell, okay. Another word. I bet Nathan may make a good guess. Or Kevin.
Can you repeat the question?
When closed shell, when you can put electrons on the same orbital, just up and down paired electrons.
Singlet?
Yes, right, singlet. But there are situations when you have only one electron on the orbital, right? So number of electrons up and number of electrons down are different, right? And this is called doublet because it can be up or down, 2 states degeneracy. But there could be situations when there are like 2 unpaired electrons, and then there are triplets. So this now I guarantee that Mary knows about it because she is aware of using letter U for, like, if you have Hartree Fock, you put UHF at the top of your method. And U stands for unrestricted, that you can put spins up or down. So we need to verbally recall this density of states things just in case if someone forgotten, refresh memories really quick, and it is not a main goal. And then we need to build a model that will be like open shell. So the it should be a small one, and titanium hydroxide will not work because it is closed shell. So it needs to be something a little more advanced, but of about the same size. And then I will try to go over scan of reaction coordinate for the first time in several years. But if some of you will select projects, again, the main part of the course will be projects that will start about, they will start like April 1st and end when semester ends, right? So some of you will select characterization of materials as they are, and some of you may select chemical reactions when bonds are broken or formed, which is a really cool stuff for to the near and dear to hearts of true chemists. And one of more complicated ways is the transition state search that I will not cover, and we will all hope and trust that Mary will present it in the right way. And if you have recordings from last year, it was presented by Russell Hoffman. And I will cover the scan of like Gaussian keywords and operations to scan the reaction coordinate. If you have like one portion of molecule which is donor, another as an acceptor, and there is a like transmitting entity, it could be hydrogen, that originally stays at donor and then it ding, 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 enters to acceptor. So this reaction of proton transfer can be represented as potential energy, where donor and acceptor will be minima and transition state will be maximum. I don't know if you like, well, some of you may just take rest or leave when I will be presenting this, but originally this course was designed for chemists, and let me check who feels happy with the word transition state. 2 halves. 5. Who feels very unhappy? Who never heard occasionally the word transition state? 1. Who is vague and maybe heard but never used? 1, 2, 3. Okay, so 4. Now I'm wearing a hat of, I don't know, organic chemist. If you do have chemical reaction, you can assign distance. For example, the following is redefined again and again, very differently for each reaction. But for reaction like this, you can assign distance from donor to acceptor as reaction coordinate, which will grow as reaction goes on. And then you put this reaction coordinate on x-axis, and on the y-axis you put total energy. And then your initial state before reaction is called reactant. After reaction is done is called product. And the top of the barrier is called transition state. So if you are looking forward to describe chemical reaction, it is vitally important to know the energies. How high is the barrier? How high is the energy of transition state? And there are different opinions what is computational chemistry. So some people believe that finding transition state is the main goal of computational chemistry. I wouldn't agree, it is much broader, but for some people it is a major part of this activity. Okay. So about homeworks, the orbitals for perovskites were challenging, right, for most of you. Who was able to draw orbitals of perovskite? No one? Who just got some images?
I got a flat image.
1, 2. Okay, so in the menu for the methods, one need to go down to the menu and select larger basis sets than the one to DZ. For heavier elements, one just need to explore which bigger bases are available. So it's a standard error, and do not worry if you didn't complete it. It was kind of a trap just to show that we need to make versatile browsing in the space of parameters for the code.
Critical thinking.
Yeah. Another relating to the homework. I also noticed an error that maybe most of you were not doing. So, how do we connect these two titanium atoms to form a dimer? What are other opinions?
Double bonds.
Double bonds, oxygen, any other opinions? I just saw something not wrong from common logic, but very theoretical from the chemical point of view. Okay, I will not disclose the name, but those of you with like monomer was having oxygen and then hydrogen, right? This monomer was also having oxygen and hydrogen. So in pure logic, why don't we just connect these two oxygens together? So what is wrong with this thing? Huh? I don't know how to explain it, but if I would take freshman chemistry and write it in my test, I probably get expelled from the department. So if two oxygens are connected, it's just O2 molecule, it's stable in itself and it will not bind anywhere. If the oxygen works as oxidizer, it pulls electrons from reducing agents from like metals or hydrogen or carbons. And then if it is already making connection to metal, then it would be much more natural to connect to directly to titanium. Okay, so I hope the unknown attendee of the class agrees with it. And I will not turn back so that I don't smile. Okay, and in previous, yes.
So we initially made it just like this correct way you have it, and then towards the end, for some reason, there was like an extra connection between the titanium and titanium.
Oh, you may have seen a line.
Yeah.
But lines mean nothing.
Okay.
As soon as you depart from force field molecular mechanics, lines are just abstraction. They do not change results of calculations. They do not just forget about lines. It's just how to say
Visualization.
Artificial?
artificial visualization tool. Thank you. I am honored to be in the presence of educated and thinking about. Yes, artificial visualization. Good. For the density of states, give me a little hint if you're hesitating, make it secretly, if we need to refresh the scripts that are making. We should?
Are we gonna discuss the Fermi level? Or is it too advanced? That's for later?
No, let's discuss it right now. So, who can define what is Fermi level? Please.
Fermi level is the point halfway, the point where all electrons, the energy level where all electrons are in.
It's the halfway
Explaining it
point.
very poorly.
It's the halfway point between the occupied and
I can.
It's the
explain
point
my-
where at absolute zero, the energy level where the highest electron is.
Okay. Energy level where highest electron is halfway between HOMO and LUMO.
Which is, they normally draw halfway between home and LUMO.
So the term Fermi level comes from Fermi distribution. So Fermi distribution is the probability of finding an electron at a particular energy state at a particular temperature. So and absolute temperature. So the value of the Fermi distribution function should be 0 for conduction band and 1 for valence band. That means there is no electron.
Okay, Fermi level is energy where Fermi distribution will not change upon increasing temperature. And you see, Fermi level is a level that will be half occupied at infinite temperature, or at high temperature.
How do you know you have it in your density of state plot?
You cannot extract Fermi level from density of state plot if you do not know what is the absolute number of your HOMO and LUMO. So before you define Fermi, like in chemical systems, in isolated molecules, we will not deal with Fermi distribution. It's like a little strange because energy offsets much higher than thermal quantum in most of them. So the definition by Sudipto is correct, but it is more for like metals, semiconductors, physics.
So it's the
materials.
absolute difference between the two?
I'm going to write something, but do not quote me because there are different opinions. So not for the record, but as a good starting point. Like you need to find number of HOMO and number of LUMO. Then you find energy of the orbital number HOMO, which you can report as ionization energy. Then you report energy of the level which corresponds to number of LUMO. And LUMO is typically HOMO plus 1, right? Electron affinity. Then you report energy of LUMO minus energy of HOMO, and you tell it is gap. Right? Another descriptor if you are from data science community. And then you do energy of LUMO plus energy of HOMO divided by 2, and you define it as energy Fermi. Okay? So you have heard variety of definitions, and some people may object, but it's not wrong. It's just there is a diversity in definitions. Okay, and for each system you are describing, it's a good practice to record and report these numbers. If you need to be a single author, if you want like write papers, like paper per 2 weeks, and you are not ambitious for like top ranked journals, you select like any molecule you like, and you look for mid or low impact journal. You just compute these numbers with one method, then you change the method, recompute these things with another one, and make table how the observables depend on method, like different DFT functionals, correlated methods like MP2, Hartree Fock, and it will be. It's not a super big science, but it is a, like bread and butter that someone in the community will need it eventually. So you just do calculations, report, submit. You may be lucky with getting accepted. Good. So whew. So I do not trust to my memory, so there is a little memo for memoryless people like myself. And there is an example of the name of the script. So I'm doing it per request. So if there is a log file, you let's see if I have some. Log. Okay. So you type Perl, the name of the script, space, name of the log file, and then how many? Four parameters. The first one is number of grid points, resolution. Another one is width of Gaussian, and then two numbers, how much below and how much above HOMO and LUMA. So after launching this script, you're getting 4 additional files. And looking on the E underscore, you see the list of files in a little more reasonable format. So, occupied, unoccupied, right? This is this perovskite model. And I also did the same wrong step as all of us. Did it with too cheap basis set. Simple, but it converges. It shows gap about 2 electron volt. Ionization and affinity, you see numbers here, and you just track down where occupied changes to unoccupied. And if you need, do you need me to speak this up? No, the rest is clear, right? You just
There's a typo.
yes, thank you. New plot. New prog DOS. And in order to run it, one needs to rename so this command will it was Gauss. So one needs to rename file created DOS underscore with name of your file .log. You need to copy it into the generic name. Just a second, I see your hand. And then there appears the .ps file that you convert into PDF. By the way, if you're not sure if you have graphical terminal, which maybe we can, but let me show how old-fashioned school works. Like if you do not have graphical connection. So I can plot things in this obsolete format. So Homer and woman. Yes?
Could you send us the CS for...
What is CS?
Or the CS for... Yeah, the CGM
Oh, just
molecule that you'll have, because we were having issues putting the cesiums in the correct spot. We were doing that.
Oh, okay. But please be my guest and just visit this directory and take it. Okay? Yep. All open, no secrets. So enough for those. We are done with this refresher, and we are done with Koopman's theorem. Right? Well, I do not need to ask the whole class. I need to ask Queen. Enough about Koopman's theorem. Yes?
What was Koopman?
Huh? Who is Koopman?
No, what part was Koopman? Like you're saying the homoluminal portion?
You shouldn't care. You're not presenting the subject.
I'm asking for my buddy.
Oh, okay. So the Koopman theorem is that energy of highest occupied and lowest unoccupied orbitals correspond to electron affinity and ionization energy. That's it. And the rest was like mumbling and background information, just in case if someone is not super excited about electron affinity and ionization, redox potentials. Right. Okay, so for open shell orbitals, let's discuss together what to draw. And please, do you have MobaX term open?
Mm-hmm.
Yes.
Oh,
Yes? Okay. So let's design a molecule. What if we take what is Aufbau of titanium? Let's look into the P table, just in case. I believe I remember it, but it's better to.
AR 3D2 4S2.
Oh, good. Thank you. So argon.
3D2 4S2.
3D2 4S2, right? So 4 electrons on the outer shell. When we were practicing titanium hydroxide, all of these 4 electrons were removed from titanium to oxygens, right? Correct? But other situations when one removes not all of them, but partially. So I'm going to design a molecule, and it is a little lie. I did work with it before, but here's the logic. Please please give signs those who took some inorganic chemistry. 1, 2. Who is taking it currently? Who is exposed? Who has some exposure to inorganic chemistry? Okay, thank you. I will ask you to close ears so when I will tell doubtful, heretical things, so that you do not criticize me. I'm joking. Please criticize if I'm telling something wrong. So when, and it's not part of the class, but we cannot avoid it. It's like a background information that we all will need. If we do have chemical compounds that include transition metals, there are several aspects that determine both energy and chemical bonding of this metal. So, due to shape of these d orbitals, there are several that are always part of the transition metals. There are several spatial coordinations that transition metals like to take, right? And when we do computational chemistry, if we suggest wrong geometry, wrong configuration, it will just give unreasonably high energy. It will be not stable. We as humans can design anything, but if we design wrong, it will be just non-realistic energy. If the information from nature or from computations is fed into cheminformatics, then it will be just a set of rules. What are allowed geometries and allowed oxidation states. So I'm telling again the thing that was already recorded and that David presented here, okay? About coordination of titanium or transition metals in general. So there are not very many, less than a dozen typical orientations. Like all transition metals like to have more than one bonds, and typically bonds are arranged with some level of symmetry. Like with most preferred tetrahedral and octahedral, right?
Point groups.
Good. Good. So in order to, like if we design molecule including transition metal from scratch, if you don't have any information, one needs to take into account both like occupation, how oxidation, multiplicity, and coordination. And some of them can be dominant, some of them can be least important. So, what if we dissolve titanium chloride in water? What are you expecting to get?
Ionic and ionic.
Huh? Just repeat it. What will happen with chlorine? Huh? I'm not sure, maybe not enough. Any other opinions?
There's room for it to coordinate with more.
What are the possible options?
We can have TIs, we can have two OHs, or actually even OH.
And it is much more. You have supply. Water is not
So
limiting
you're
right
gonna
now.
have like
Like
two-
100 or whatever, or like 6.
Well, the TI is coordinated by 3 in the plane, and then it will have like that, like proton. I don't know if I'm
TI is coordinated, yes. So I know the answer, but I do not know how to explain it. Let's just, David, what is your opinion? You are top expert in organic chemistry in this room. Which scenario you may expect? So, sometimes there are chemical reactions, and sometimes there is just solvents with ions moving freely. Yes, perfect. Titanium chloride will dissociate on titanium 3 plus and 3 chlorine minus, right? And it will be surrounded by supply of H2O by water, right? So chlorine counter ions will float away, and we can forget about them because they will not contribute neither to HOMO nor to LUMO. And then we will consider a complexation of titanium 3 cation with water. And because only highly symmetric coordinations are possible, it will coordinate with water in one of the most symmetric octahedral fashion.
So the first step is always, like in those kind of scenarios, is going to be dissociation, when you have that kind of setup.
Yes, it is a very reasonable guess. And if we would dive much deeper into details of Gaussian, we will say goodbye to Gaussian very soon. But there are additional options for mimicking and modeling solvent, which is really important for small molecules. So we are going to put 3 plus titanium and octahedrally coordinate with the water. And
Are those going to have plus charges on those occupants? The OH2 plus?
so we put a bracket, and the whole complex will be 3 plus.
Oh, okay, got it.
Okay?
Realistically, if you're asking where that charge is, it's about half on each water.
Well, the
That's really not all.
no. Titanium itself will be 3 cation.
Yeah,
Water
the
will just
charge itself will expand when it's in this octahedral shape, and it will actually go on to the bonds between the water.
Well, we will assume that near somewhere apart from this, 3 chlorine anions are floating to compensate this charge.
Which, yeah, for what we're doing is not a big deal where the charge is, but that's where we're
Okay.
being asked.
And if this complex at all, and titanium ion specifically is cation 3, then we remove this s orbital and we remove 1 d orbital. So it will be 1 unpaired d electron. And the previous setup, where we did like Hartree-Fock charge and multiplicity 0 and 1, will not work. We will need to modify this keywords, and we will get different style of output, and we need to specific commands to plot orbitals. Okay, makes sense? Let's check who should listen to it and who can, and the rest can skip. Oh, David. So it's only David who needs to listen to it. Okay. I didn't knew it, but it kind of makes sense. So feel free to do whatever you like. Maybe work on preparing your slides if you didn't ahead of time. But right now my target audience is David, and I will try to build this model and show how the orbitals for open shell configurations differ from the closed shell configurations. Okay? Oh, please make it circle.
Yes, I will eat all of that. No. We're cold.
Okay, so what I did, removed, first placed oxygens, removed bonds, then made it H2O, and then restored coordination bonds and did like fake optimization with Broom. And now we are going to Gaussian calculation. We are staying with energy. We go for the cheapest for transition metal, and see it will need to go for charge 3 plus, and then it immediately, you see, it immediately prompts that if the charge is odd, then there is no option for singlet, it will be doubled, right? And then let's see how far it goes. So let me walk around and see if, how much you enjoy drawing this octahedral structure.
So we have to make that in JAWS view and then make a density of states plot.
No, just run single point calculation and then plot orbitals.
Okay.
Okay?
are the oxygens.
Correct.
And then attached to the oxygens are hydrogens.
Yes.
Thank you.
Well, I'm trying to get that on my desk.
Which functional basis are we using? David, what functional basis are we using?
I'll send you some.
Okay, that's the basis set, what's functional? Oh, we're just doing single. Yeah, okay, never mind.
Yeah.
Is it Hartree Fock?
Yep. Oh, you don't need to forward it. I'm just looking for what is going on. Which is repeat the same command again and again.
Okay. So I have a request answer.
Also, we need to shorten calculations quicker.
I'll send you the link for this because I used to use it.
Question.
Yes.
Is this related to what I need to look into?
Yes.
Okay, I'm on the right track, okay.
This is kind of like.
Yeah, and you full me for your chemical intuition.
I have.
David has converged results. Heroism.
I do too.
Okay. So they may give you better help than I.
You get this?
I haven't run it yet, but that's
Okay.
what my structure.
Yep. Are you changing it to hard to retrieve off the
We can. It's we will start DFT very soon. It doesn't matter.
Are we editing? I'm kind of got lost on what we're doing.
I will
Oh,
I will
okay.
come back. I just need very short. Okay, so I'm inviting everyone to do very silly and non-intellectual work. For the unrestricted calculations, scripts are not available today for Gaussian. Later, when we will be doing investment DFT, I will provide scripts. So instead of scripts, we will do something just silliest thing a human can do. So if you open successful output of Gaussian Hartree-Fock with charge 3 and multiplicity 2, right? And if you don't, feel free to borrow it from your colleagues, share it. Like ask who wants to share and just distribute. Right now our goal is not to complete results. You just got your experience how to do it, and if someone got quicker conversions, do not spend time. So if you open, and David, I want to give you credit, I've borrowed yours.
Okay.
Yeah, mine is working as well, but your converged quicker, so it depends on the initial guess. So if you don't mind, you may share with others, or just give permission anyone to take it. So if you open .log file where your multiplicity was different from 1, right? You can either put multiplicity different than 1, or at the top of your, or you can edit your input file before submitting to Gaussian and put letter U in front of your method. Like if it was HF, Hartree-Fock, you put UHF. If it was like Bisrelief or LDA as a density functional, put U LDA or U Bisrelief. So when you open, you'll see your old friends in a sarcastic sense. You'll see large number of orbitals. Okay? So what you will recognize, there are occupied and virtual, right? But occupied and virtual. But you see that they will happen, they will come in twice. Once with prefix alpha, and then repeat again with prefix beta. You see it?
Yep.
Do you understand it?
One's fake and
Like
one's real.
not understanding like what you recognize what is seen, but do you have an idea why it is needed?
there's subgaps, right?
I do not like to erase things from the board, just fearing that something important was there, but I'll probably erase things here. Can I? You already did the screenshot if you need it. So typically, we do have orbitals, and we populate them with electrons with spins. And here we know for sure that the configuration is double, right? Yep. So in some sense, this orbital serves both as HOMO and as LUMO, as occupied and unoccupied. How do we know that that when it serves as HOMO and when it serves as LUMO, it will have the same energy? So let's not suffer intellectually. I'll just offer one of the options. So what if we will draw two orbitals instead of one at each energy, and then we will call them alpha and beta, and for alpha orbitals we will put electrons with spin up, and for beta electrons we put electrons with spin down, right? So the main reason to do it is that due to equations that are behind this theory, one can find that the energies, when it is the same number of orbital, when it is filled with electron or not filled with electron, can be different, or maybe opposite. It will be a little higher when it is unoccupied. Okay? So there will be two sets of HOMOs and LUMOs. One HOMO LUMO alpha and another HOMO LUMO beta. Okay? So now let me invite you to do a very silly thing. I hope that I will never ask you to do this again. So let's manually count orbitals in the output file. Do not worry, not all of them, only occupied. So let's start from occupied, and look, here is the border between occupied and unoccupied. Let's count what is the number of this orbital. We can either count them one by one, or just multiply number of rows by number of columns. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 7 by 5? Huh? How many? 35. So those are alpha. So this will be orbital number 35, right? 35 up, or 35 alpha. Now, let's look on the beta more eyes here. Beta orbital set. So we know that the orbital here will be occupied and next one unoccupied. So what will be the number of this orbital? Last occupied, highest occupied for beta. Like if there will be another orbital here, it will be 35. This one less, 34. So the orbital here, lowest unoccupied beta. So HOMO beta equals 34. HOMO alpha equals 35. Right?
And it should follow, so the numbers should follow from when you look at 35 to 34, right?
Well, we may want to compare the orbital number 34 for alpha and beta. Well, the difference is not drastic.
Right.
It's like in
Right.
third digit, but there is difference,
Sure. Okay.
right? And we can compare energy of this orbital, highest occupied minus 1, 0, 0, with LUMO of the beta.
Right, it's
And
beta.
this orbital number 35 for alpha and orbital number 35 for beta have drastically different energies. Remember, it is in Hz, not in electron volts, right? So, was I wrong or right? This one is bigger, so the unoccupied orbital drifts up,
Okay.
right? So this is the reason to have the U unrestricted. This is the reason this is pops up when you do non-singlet calculations. And it would be like, I don't know how about you, but I would be really curious to compare not only the energies, but also the shapes of orbitals. Like the orbital with the same number, will they look differently or similarly? So I would put number 34 for alpha and beta, number 35 for alpha and beta, and number 36 for alpha and beta, like 6 orbitals.
And this is where you go to the P table and look and see if the shapes kind of look.
Yeah, well, let's just draw and check what goes on. So, who doesn't have the file? Everyone has. So please talk to each other and share. The goal is to draw, not to achieve convergence. If you didn't converge, if you didn't achieve convergence by now, do not worry. Take the file either from me or from David. I took it from David. And maybe I have some successful calculation already by now, but it's secondary importance. Yeah, I have converged on my own, but still, David is the winner in this race. So what do? I do have numbers. Again, remember beginning of our discussion today, one always needs to identify number of homo and woman. So I did identify it. Now I did the form check, right? Form check, name of the file .chk, and here's a little different. It is not documented, but we'll figure it out. So the difference is only in one word.
So if we have his file, the next step is to calculate or just have it?
To calculate the orbitals.
34 was our HOMO. Right?
No, 34 was HOMO minus 1 for alpha.
Oh, okay.
So, and occupied are expected to reside on oxygen. So the only difference in the format of using the command, so kubegen space 0 space, before we used molecular orbital equals number. Here you put A for alpha and B for beta. And it just makes sense to name files accordingly.
So you did 34, 35, 36, right?
Yes, and I redo it over again for A and B, for alpha
Oh,
and beta.
got it. So you did, okay, got it.
And there is a really big danger to get lost in details. So I'll probably will record them right away. By the way, did any of you found the way how to plot orbitals without purple background?
Yeah.
So what is the command to remove the purple?
Oh.
It doesn't matter right now, but you can
I just
look.
save it as a picture. That's hard.
Okay.
Well, you can change it.
Change the background color.
Oh, that's
Yeah,
right.
change
Yeah.
the background cap.
Oh, you
Yeah,
already
that's
told.
right.
So please, next time plotting orbitals, try to follow. And if you don't remember, look what Ben was showing, right? You was showing so quickly everything, literally 3 minutes or shorter, so that it may have been forgotten in our minds. Like highlight, and I repeat once again, my main message is not the details of the method, but how to make white background. So most interesting will be 35.
showing us are the isosurfaces again, or?
Yes. So you may continue to explore, but if we are drawing this orbital number 35 alpha and beta, which are occupied and unoccupied, they're not identical. They have similar character, but they are oriented different in different planes. So you see that they're different orbitals. They are not coinciding. So even if you skip the spin degree of freedom and just multiply them by each other, they will be like they are orthogonal, right? So different things. And here both of them are have primarily character of d orbital and titanium with some admixture of oxygen orbitals. But when you come into a situation when you do projects and you need to analyze materials with metals, it makes sense to draw two sets of orbitals or two sets of HOMOS and LUMOS if you don't have steam for more, because they can show very different insights, and they will also any which let's chat and discuss which systems typically are open shell. Transition metals, yes. And the open shell transition metals, they're typically magnetic. In very literal, simple, stupid sense, if you just approach fire of this material with a magnet, it will attract. Which other compounds experience open shell configurations? Just launch your chemical imagination. It's typically symbolized with dot.
Radicals?
Yes. So very often radicals are open shell. And any if it is not like transition metals feel happy in open shell, but organic hydrocarbons also can be temporarily in the open shell configuration, but then they become highly reactive. They will either burn or oxidize something, and they will exist in such state not long time. Any questions about open shell configurations? David, you'll be able to teach everyone?
I hope so.
Good. So, huh?
We'll find out.
Okay, we will. Let me. I hope you have a little bit of steam, although we're kind of approaching the. No? I need to take some measures. Measures.
Measure.
I do not have much, but you can split maybe one per 4.
Thank you.
Sure, split sure around. So I'm going to cover subject like right now. Relax, everyone except Mary. It will be subject that she already volunteered to present. Again, please remind us. I have something to send. I'm just too excited about presenting. So, among the subjects, there is scan reaction coordinator. So for those of you who may do reactions like combustion, burning, and I promise during when you will be doing projects, when you will decide which projects to do, some of them will include reactions, and it could be a big temptation to do it. Those are really interesting subjects. So I'm going to show a set of slides first, just in case we are limited in time, and then I will do the practical steps and hope that you, at least Mary, will be able to follow. So I did something that was my little project just for entertainment. So lean back, relax, right? I can share the slides. So this project is not complete. Some of you may select it to complete in the class. Space exploration doesn't have the powerful ionic or nuclear engines. Most of the engines that take humans to orbit are chemical combustion. And the launching spacecraft is a highly risky endeavor, because when you mix fuel with oxidizer, they may or may not ignite, and if they do not ignite, it is a big disaster. They mix and become combustible, and then any spark will blow everything up. So there is no optimal ideal solution, but one of the solutions is to use chemicals that ignite on mixing automatically, self-ignite, and then there is no misfire. Like, they're highly toxic, and we do not do it in cars, but otherwise we could fill cars with such mixture, and then even if you do not need the spark plugs, it will just run without ignition, just start pumping. So one of the molecules is derivative of hydrogen, with nitrogen with either hydrogens or methane, and another is the stuff that becomes nitrous acid if you dissolve it in water, nitric oxide. And one of the steps towards combustion is proton transfer from donor to acceptor. Okay, so it is interesting to build such diagram. Building such diagram will tell whether it will self-combust or not. The answer is known, this will, but just in case, when we check how tall will be the activation barrier. So if you build a model that you want to scan, and later on I will try to repeat, and those who are interested may try as well. So in the job type, you jump to scan, and then upon you select it, there will be another submenu. And you can try all of them, but the last one, most reasonable, less problems. Relaxed, redundant coordinate. So it means that relaxed, it means that at each time step it will adjust positions of all ions, not only the one that you are moving. And redundant coordinate, it means that position of selected ion will be redundant. You will run several replicas of a model with different position of this ion. So if you select it, then Gauss view will complain to you. It will take, hey, for your model, you didn't specify which coordinate you are going to go over. So you need to use redundant coordinate editor. And I was, when I was doing it for the first time, I was shocked, like, where it is, where? But there is additional menu in Gauss view that is named exactly this way, redundant coordinate editor. So if you go to edit, and then there is a pop-up menu. And here you click add. So you have nothing, you click add, and then there appears new line which gives you option. So same as, remember when you were drawing models, there is an option to change interatomic distance. There is a option to change angles between bonds, and there is an option to change steric, how does call it? Twist and sophisticated word. It's all correct, but there is another one.
I know you're saying
Well,
stereo.
It just went out of my mind. No.
No.
Angle. Okay.
Strain?
No. Okay.
Stereo projection?
No, it may not start with letter S. But when you have like
Stereochemistry.
no,
No.
two bonds in different planes. When you do isomers, it's really useful. You were presenting and everyone was using this word.
Symmetry.
No. Let me quickly show it in GaussU, and you may refresh it very quickly. So this symbol, dihedral.
Oh.
Dihedral, yes. Okay, so there are several parameters. Even you change position of like one-dimensional change, you may change the dihedral or something else. So you need to be more specified. You click on this unidentified, and it will give you these options, like change Cartesian coordinate, just randomly change projection, or bond, angle, dihedral, and other things. So I selected this simplest one, bond, and then you need to go back to the image and click bond between what and what. Okay, so you just select two atoms and select a bond, and then it's not the end of the story. There is a way to do it in like a couple of lines in the input file, but it is a good introductory. So it selects coordinates of which ions, which atoms from the model, and then you need to add the way to click on the add and tell what you want to do. So instead of add, you put scan coordinate, and there are several other options, which gives you a variety of
Why would you want to
to
kill
play.
the coordinate?
Why do you want to kill a job in Linux?
Okay, yeah.
So someone needs me. It's advisor of 4 people in this room. And then there will be, like, if you do nothing after selecting scan coordinate, it will do nothing. It will take 1 step of 1 angstrom, or like 0 steps. Do not use this by definition thing. So replace it by the idea that seems reasonable for you from your chemical intuition. So if your original bond length was too long, you can increment negative to make it shorter and shorter. If it was too short, you can expand it. And then put number of steps. Gauss view and Gaussian itself can do multi-dimensional things where you can like change all atoms at once, but it will be very expensive. You can generate multi-dimensional potential energy surfaces, but for practical applications, it's much easier and simpler to have one-dimensional and do not put large numbers. Like this job will take like maybe overnight on one CPU. If you do parallelization, of course you can speed up. But if you need more coordinates, you just click add and have several Like there is a chance to make two-dimensional, three-dimensional potential energy surfaces. And when you done it, you click submit and give some reasonable name. So then suppose a night is over, or whatever, 24 hours, or how long it takes. Then you open the log file and click on the results. It will give exactly the thing that one needs. So there is a way to extract it from the output file, but for those of us who are in rush and do not have time to write scripts and extract raw data, it already draws. So it shows where one started and where one ends. So the position of the proton between nitrogen and oxygen is scanned. And then it is end of mechanical part of the work, and then you start thinking intuitively as scientist, chemist, material scientist, physicist. So there is another menu in the output. When you open output file, .log file, you typically see the structure. That's it, right? And then you go to menu and request summary, orbitals, whatever. There, I didn't put it here, but at the top of the window, there will be another menu with number of snapshots. And by browsing through this menu, the red circle will encircle different points on this potential curve, and will show you different parts of different intermediate configurations. Okay, I plan to show it. It will not take much of our time. And then you can identify the, so this one is a product, minimum when proton is closer to oxygen. And there is a reactant when proton is closer to nitrogen. And in between, there is a really small activation barrier that is definitely easy to come over with thermal activation. And then there is an intermediate, and there is another barrier. Yeah, good night. So 2 transition states and 1 intermediate. Yes?
For mine, can we suggest a new molecule so I can try?
Oh, absolutely.
But I don't know if I would pick
Would be reason like maybe break water molecule on H and OH.
Okay.
Simplest example.
Okay.
Right? Then it will like be done in a minute.
Okay.
Or maybe methane and chlorine, or methane and oxygen, like for combustion. Here is just one of the initial reactant state when proton is closer to nitrogen and it is far away from nitrogen oxide. Okay? So try doing something like this and explain it in a way so that anyone in class who needs it may repeat it.
You can save the movie, so you can actually
Yes.
play it again.
So it shows how it goes over different configurations. Okay, here how the output look like, just in case. And one may focus on narrower part so that one does see that it is not a straight line, but there is a substructure. And the energies are not super small, they are in heart rate, so it's about 0.5%. So it's comparable to thermal energy. Okay, I'll stay here to answer any questions, but keep working on your presentations. Is there is everyone ready to present tomorrow? Just talk to each other what you prefer. I can even leave the room so that you are biased, and then we may practice votes.
Yeah, that's what I'm thinking. I really need a little bit more time. This week has been terrible. So I think we should do it Tuesday. What do you guys
Not
think?
my week.
But this class with other classes sucks.
Okay, what do you guys think? Tuesday?
I think we should just like get it over with. It's only like 3 minutes long. It's like not a lot of time. We can just like look at his recordings in like 2-3 minutes. Just copy what we need from there, and that's it.
If I got 2 exams tomorrow.
Yeah, that's the thing.
I have an exam on Tuesday.
Okay, who votes currently to?
So
We'll find out.
Okay.
is there like?
Okay, we got some ideas, so I guess we'll just take a vote.
Well.